So we introduce a definition. What's the constraint minimum? Suppose f is a function on omega, and m is a subset of omega. A point x0 belongs to m is a minimum of f under the constraint. Constraint m. So this is omega, and the m is here. So x0 belongs to m. X0 is here. We say that this point is a constraint minimizer. Maybe I will replace this sentence. X0 is a constraint minimizer. Of f with respect to m. If it is reasonable to see to define this concept that x0 is the minimum value of the value of f at x0 is the minimum among all points restricted to m and near x0. That is, there is a neighborhood of x0. There is a neighborhood of x0, so that the value of f at x0 is the smallest one among all values, among all points in the intersection of the neighborhood of which m, that is here. Okay, so if there exists a delta positive such that fx will not less than fx0 for any x in the intersection of the delta neighborhood of x0 and m. So this is a reasonable definition. Okay. So in the theorem, we simply say that x0 is a minimum point of this function. Minimum point of this function. That is, we consider f as a function defined on m, then x0 is a minimum. That is, for point m1 m and near x0, the value of f at x0 is the smallest one. So this is coincide with our constraint minimizer, our definition of constraint minimizer we just introduced. Okay, these two are coincide, they are equivalent. Okay, maybe I make a summary. F x0, maybe I stated this as a remark. x0 in M is constraint minimizer of F with respect to M. This is equivalent to say that x0 is minimizer, local minimizer of F considered as a function of defined on M. Of course, our F is defined on a larger set omega. M is a subset of omega. But when you talk about constraint minimizer, that is, constraint minimizer is precisely the minimizer of F considered as a function defined on the constraint set M. Okay. So we prove the theorem. Prove of Lagrange theorem. We will provide two proofs. We will using the geometric proof. So that x0 is a point in M is a minimizer of the constraint function. So this is M, and our x0 is here. That is a minimizer point of f considered as a function defined on M. So by definition, there exists a delta positive such that if x is near x0, maybe x is near x0 means that x lies in the delta neighborhood of x0 for some small delta. But x need to be satisfies the constraint condition. That is, x also need to be a point of M. So if x is the intersection, then fx will not less than fx0. That is, we have a small neighborhood around x0. So that when x is a point here, the intersection of this small neighborhood with M, then fx will not less than fx0. Okay. So what shall we do next? We have a small neighborhood of x0. This is an open set. B delta x0 is an open set. So we defined a map on this set. This is interesting. Defined capital F. We define a map from this delta neighborhood of x0 in Rm to Rn plus 1. How to define this map? We have a function f omega to r. We also have a function g omega to Rn. Right? So we combine f and g together. We all together has g has n components. And then we add f into g, we have n plus 1 components. These are the components of our capital F. Okay, define such a map f by fx to be small fx, then gx. That is fx, g1x, gnx. So we obtain a map from our delta neighborhood to an Euclidean space. And our fx0 we denoted by y0, which is fx0. Okay, why this is 0? The last component of fx0 is 0 because gx0 is 0. Okay, so this means that the last n component of capital F is 0. So we have a map. What shall we do next? We want to apply the differential calculus. So once we have a map or we have a function, the natural operation is to compute the derivative of the map or the function. So we compute the derivative of f x0. F prime x0 is the derivative of a vector valued function. The row vector of this is a metric. This is a m plus 1 row and m column metric. This metric, the row vector of this matrix is precisely the gradient of the component. Okay, so we see that this is fx0 g1 x0 gn x0. The derivative of f prime x, the derivative of f at x0, that is f prime x0, can be written in this way. The row vector, the metric is n plus 1 by m. So we have n plus 1 rows of the metric. All the rows are the gradient of f and g1, g2, gn. All these gradients are m-dimensional vector, has m components. Okay, so this is the metric, the derivative we computed here. So once you have this this metric, what can we do? We compute the rank. Consider the rank. We have a claim, important claim. The claim is that the rank of this metric is n. The rank of this metric at most n plus 1, and it will not less than n, because the rank of g prime x0 is n. This means that the gradient of g1, g2, gn at x0 is linearly independent. So the rank of this metric will not less than n. So the rank of capital F prime x0, the rank of the derivative metric of capital F at x0 is either n or n plus 1. Okay, at least n, because the last n rows linearly independent. Okay, but we claim that the rank is n. Once we know that the rank of capital F prime x0 is n, since the last n rows are linearly independent, so the first row must be a linear combination of the last n rows. The first row is linear combination of the last n rows. Therefore, we have lambda 1, lambda n such that minus lambda 1 g1 lambda n gn. That is is 0. That is what we want to prove. So this concludes the proof. So it remains to prove that our claim is true. So how to prove the claim? Okay. So we argue by contradiction.